Okay, so let's look at some basic filter design concepts. So just as a reminder, low-pass filters, or filters in general, they come after the sensor's analog signal and before the data acquisition system. So you put a filter in there to change it before you record it. And ideal filters usually have amplitudes that range between 1 and 0, and they have a very steep line here, a vertical line at the corner frequency. And we can't have that vertical line in practice, but this is what we would like every filter to have. And we use this frequency response graph to find the amplitude, the gain of the filter as a function of frequency, and it gets multiplied in, if we have a sum of sines like we would get from a Fourier series or an FFT, we can write the signal that way and figure out what the amplitude of the filter is, and it keeps parts and eliminates parts. If you're dealing with a real filter, a practical filter, you also have to include the phase shift, and we can't go to 0. Here is a practical filter, a low-pass filter, first-order low-pass filter based on the inverting op-amp. So we looked at this in the last lecture, and this is the frequency response where we have the gain in decibels on the y-axis and frequency on the x-axis, and it's a log scale for it to look like this. And the slope of the curve, we can approximate this as a straight line after the corner frequency with a slope of -6 decibels per octave, where an octave is a doubling of the frequency. So this plot here is one way to see the results of the filtering. And if you have this graph, you can just read the amplitude off the graph as a function of frequency. But we also have the equation that created the graph. So this is an equation for an nth order low-pass filter, a Butterworth low-pass filter. And the book has all of these equations derived in a nice way. But the gain is 1 over the square root of 1 plus the ratio of the frequency that we are interested in divided by the corner frequency to the 2n power, where n is the order of the filter, so an nth order filter. So we've been looking at first order filters like the RC circuit. That's an n of 1. And if you need a higher order filter, there are circuits for higher order filters, but you can also just run the output of one filter into a second filter, and that becomes a second order filter. So the number of filters in series is another way to think about what order you're at. So as an example, we've got this first order filter, and looking at the frequency where f is 8 times the corner frequency. So f over fc is 8, which would be used in this equation, or we can also think of it as 3 octaves. So the first doubling is 2, and then 4, and then 8. So 3 octaves to get to 8. So if we plug 8 in here, we get this equation. So the gain at 8 times the corner frequency for a first order filter is 0.12. And if we convert that gain to decibels, we get -18 decibels. So you can see we can use the equation to get an exact number, or we can use the rough shape of this plot, -6 decibels per octave, and the number of octaves to get the gain. So either way, you don't generally do both. So here is another example using this equation for the gain of a filter. In this case, we have a filter designed, so it's a first order filter with a corner frequency of 150 Hertz. So that means anything below 150 should be kept. Anything above 150 Hertz, any of that frequency content will be attenuated, made smaller. If we start with this signal into our filter with an amplitude of 0.5, a frequency of 1200 Hertz, because we've got the 2 pi here, so this total thing is the frequency in radians per second. we want to find the amplitude after the filter. And we're way above the corner frequency, so we expect the amplitude to be much smaller than the original amplitude. But we basically just plug in f over fc, 1200 over 150, turns out to be 8, so we know that the gain is 0.124 from our previous slide. So the amplitude of V out is going to be the original amplitude times the gain from the filter, so 0.5 times 0.124, so we'll get 0.062. So it's much smaller than the original amplitude, which is what the low-pass filter is supposed to do. If you were going to complete this calculation for the final sinusoid for V out, you'd also have to calculate the phase, and there's an equation for that in Chapter 3. Most of the time with filters, we're trying to make something go away, and if the amplitude's small enough, the phase doesn't really matter because it's gone. So looking at filters in general, there are different topologies. So Butterworth is a kind of filter, very common kind. And this is a graph of the gain in decibels of Butterworth filters versus frequency. So it's the frequency response for various orders. So this is a first order line, second order line, fourth order, eighth order. We also have this equation. So you can use the graph or you can use the equation. You should get the same results. So again, if we're looking at f over fc of 2, that's 1 octave, is when you double the frequency. So if we go f over fc, this is 1, 2, 3, 4. So 2 would be here. A first order is going to be -6. So -6 decibels per octave roll off. F over fc is 4. That's 2 octaves, so we expect 12. So 1, 2, 3, 4. Up here we're right about at the -12 tick mark, and so forth. So this plot matches our rule of thumb, the roll-off, if we approximate this as a straight line up to the corner frequency and then a straight sloping line, it has this slope. Or we can use the exact equation or a more exact plot like this. So it's all the same information for the frequency response. Remember, for the ideal filter, we would like it to come straight down. So higher order filters approach the more ideal shape. There are other topologies that you can use as well. So this is a Chebyshev filter topology, and it has a steeper response, especially near the corner frequency. They all come down pretty sharply. So more ideal in this cutoff region above the corner frequency, but you get this thing called ripple where the gain isn't constant or smooth below there. So this is the part you want to keep, and it's actually being affected. So there's a trade-off between filtering aggressively and keeping the good stuff. Bessel is another topology of filter design. It has a much smoother, less aggressive cutoff than the Butterworth. There are equations for these in the book too. So let's look at designing a filter. So here's a low-pass filter, just the regular RC circuit is a first-order low-pass filter. V in comes in here, V out goes here. That's why we do this one in circuits and lots of other places. So with the filter design, you're choosing the order. So if you use this circuit, it's a first-order circuit, but if you ran 2 of them together, take the V out from one and run it into the next filter, that would be a second order. The topology, or the circuit, whether it's a Butterworth like this one or Chebyshev, etc. And the other main thing you have to design for a filter is the corner frequency. So for this RC circuit, the corner frequency is given by this equation. So you pick the values of R and C for the frequency that you want in hertz. And again, the gain follows this equation. So our goal is to keep the useful frequency bands. So that's usually by choosing appropriate FC and eliminate the unwanted frequency content. So noise in a signal often comes from power supplies or vibration, and it tends to be high frequency. So we often use low pass filters for high frequency noise. And we also want to filter out anything that would be aliased if we're using a digitally sampled signal. So we have to follow the sampling theorem and guarantee that nothing greater than FM can get into our system, and that also requires an anti-aliasing low-pass filter. So low-pass filters are the most common, but you'll see other ones for different reasons. These equations and graphs all come from Wikipedia. Here's a schematic from the altimeter, the altitude sensor of a drone airplane. We've got this MPX 4115 sensor that we talked about in the beginning of class. We've got an op-amp buffer or voltage follower, and this goes to the data acquisition system on the flight computer. And in between the computer and the sensor, we have a low-pass filter, and there's a little comment in the circuit design giving the corner frequency. So with a 48K ohm resistor and a 0.33 microfarad capacitor, our corner frequency is around 12 Hertz. So this is the most common design for an anti-aliasing filter. It's not quite perfect, but it works quite well in practice. So if we have the corner frequency from R and C, we know then that is a rough approximation of the maximum frequency that can get into our signal, because anything above the corner frequency gets attenuated. So that's our FM. FC is approximately FM, and so we have to sample twice as fast as that. So with a 12 Hertz corner frequency, we should be sampling at least 24 Hertz. I think the system originally sampled at around 50 Hertz. It's not quite perfect because in a practical low-pass filter, it doesn't go instantly to zero. This would work fine if it was an ideal filter, but we never can do ideal filters. So you can see in this graph of the frequency response that if you're just past 12 Hertz, this would be our 12 Hertz corner frequency, it's not attenuated very much. It gets attenuated pretty highly, pretty quickly, for higher frequencies, but there's a little bit of content that's not negligible for just past the corner frequencies. So that's what this is saying. If we sample at double the corner frequency, we do get some alias data through. It may not be there in real life. It may not have started with that frequency range, and it may not mess things up too much if it's dominated. So it's not a perfect approach, but it's very common. It's easy to understand, and it does a pretty good job. So if it bothers you that it doesn't exactly drop everything away, watch the next video, because we will be looking at how to design anti-aliasing filters to get it all the way to zero for the high frequencies. So you can guarantee no aliased data.